So this is an example of integration by partial fractions. It's going to be one of the simpler examples, and then I'll do at least one more video with more complication. So we've got a integral. You can do this for indefinite or definite integrals, but I'll make it definite just to put some interesting stuff at the end. And it's a rational function. So a polynomial divided by a polynomial. No roots, no sines, no cosines, although that you could combine other techniques with this to deal with that. And the way we're going to do that is the absolutely crucial thing about integration and derivatives as well, but especially integration, is that integrating a sum of functions is easy. They split up. The integral of the sum is the sum of the integrals. But integrating a product or a quotient is much, much harder. But it turns out we can write this integrand as a sum of much simpler rational functions. That makes sense if you think about problems where you take a common denominator. When you take simpler rational functions and you put them over a common denominator, you get stuff like this. Well, what we've got is partial fractions is exactly the opposite process. How would you split this up? And it's useful for actually a lot more things than just integrals. It's usually the first place people have a great need for it. But that process of taking a complicated object and splitting it up into much simpler individual pieces is just a great theme and a super important theme in all of mathematics. So how do we do that? Well, first, we know what happens to denominators. They multiply when you do common denominators, and so we need to factor this to do the opposite. That could often be a sticking point, and you're going to find a lot of pretty contrived problems in this section so that's not a sticking point. Okay, so the t came out. It was a cubic, but it didn't have that constant term, so it has a factor of t. That's nice. And then the rest of it's a quadratic. Still no guarantee that that's going to factor, but looks like, well, it's going to be like a plus and a minus. And it looks like it's going to be a 3 and a 4. If I put plus 4 and minus 3, you're going to get minus 12. You're going to get minus 3t plus 4t is t and t squared. Okay, so I made it pretty easy to factorize with just a little bit of guess and check. Okay, and there's more sophisticated methods. You could actually pull out the quadratic formula if you wanted to, but that certainly worked here. Okay, so here's the thing. What we're going to do is we're going to say, I think that this is going to be some mystery number over t plus some mystery number over t minus 3 plus some mystery number over t plus 4. And certainly, if you take anything where a, b, and c are just numbers, they're not t's. They have no t's in them in this situation. They're just unknown numbers. They're not variables. If I take something of this form and I do common denominators, I'll certainly get a rational function with this denominator. The question is, can I choose a, b, and c correctly so that I also get this numerator? And that, you could think that might be a little tricky. It's actually not too hard. So we're going to assume that that's going to be possible. And there's general theorems about when is this going to be possible. Well, and it turns out that when this factorization is just, there's no repeated powers, there's no repeated powers, like it's not a t squared or a t minus 3 quantity cubed or something like that, then this will actually always work. Okay, oh, and when the numerator has a lower degree than the denominator. If it doesn't, you're going to actually want to do a long division first. But I chose to have one where we don't have to do that first. Okay, so how do we deal with that? Well, the first principle is that nobody really likes fractions. So we just clear the fractions in this whole thing. We multiply by that common denominator. So that conveniently just kills the denominator on the left and gives us just the numerator. Okay, now what's it going to do? Remember this denominator. I'm going to go ahead and rewrite this denominator over here as that factored form. When I multiply both sides by t minus 3 and t plus 4, over here with the a, that's going to cancel just the t and not the t minus 3, t minus 4. Plus b, and then here it's going to cancel the t minus 3 but not the t, I guess I don't need parentheses there, and not the t plus 4. And here it's going to cancel not the t and not the t minus 3 but just the t plus 4. Okay, so this is where there's a fairly sophisticated piece of reasoning that comes in that people often don't see. Sometimes they see before this, but not necessarily. And and that is that this is supposed to be true. This is supposed to be an equality of functions of t. We're not saying find a, b, and c and some particular value of t such that this is true. This is a function of t. You can evaluate for all t. It has a certain graph. This, for certain choices of a, b, and c that are just numbers, that's a function of t. It should be the same function. It should be identical. And there's two ways to exploit that, and I'll show you both ways here, even though it'll take a little longer. One is that once you clear the fractions, this is a polynomial in t. It's pretty simple. It's just a linear polynomial. And this, once we figure out a, b, and c, will be a polynomial in t. If two polynomials are equal as functions, let me write this down. They are equal as functions of t. The only way to do that, two polynomials can only be equal if all of their coefficients, all the corresponding coefficients, are equal. So that's one way we can do this kind of problem. That's actually the more general way, and I'll show you a special way that would work in this fairly simple case. So what does that mean? Well, I'm going to have to actually expand out what the right-hand side polynomial is. So we have a little bit of algebra to do. So we got at squared, just multiplying it all out. We're going to get at squared. That's a plus 4. Sorry about that. At squared plus at minus 12a. Okay, that looks familiar because it just was the same thing as what we had started out with without the t. Okay, plus bt squared plus 4bt, and then plus ct squared minus 3ct. Okay, I'm going to collect coefficients. So I'm going to, because I want to find the quadratic coefficient, the t-squared coefficient, the linear coefficient, and the constant term. And so this is going to be a plus b plus c. That's nice and simple. T squared. Oops, not to the t. Plus, okay, what about the t coefficients? We've got an a plus 4b minus 3c, all times t. And then plus minus 12a, and that's it. So let me just write it as minus 12a. Okay. So this is a polynomial with mystery coefficients, but we know the quadratic coefficient is a plus b plus c. We know the linear coefficient is a plus 4b minus 3c, and we know the constant coefficient is minus 12a. That has to equal this polynomial. That means that, let's see, starting from the t squared, it means that a plus b plus c equals 0. It means that a plus 4b minus 3c equals 27, and it means that minus 12a equals 24. That's a nice break that this last one only involved a. In general, you're going to get a system of linear equations here, and the bigger that system is, the more work you have to do and the more sophistication you'd like to have to solve it. But in this case, it's going to be relatively simple because we're going to get a right off the bat, and then the rest of it shouldn't be too hard. So let's go ahead and do that. A is going to be minus 2. Okay, so let's just go ahead and get this copied down, but we'll plug in the fact that a is minus 2. You can see there's a substantial amount of work going on here. I think just in place, just to save a little space, I'm just going to go ahead and add 2 there, and add 2 here. Okay. All right, so now we've got a 2 by 2 system. That's not too hard to solve. And you could solve it by solving for b or c in the first equation and substituting in. It's better to practice the elimination strategy, which is I'm going to triple that first equation, and then I'm going to add that to the second equation, and I will get 7b equals 35. Now, usually you're going to get a fraction, but I wanted to make the numbers work out nicely. So b turns out to be 5. So we got a, we got b. Once you got all but one variable, it's going to be easy. C is just 2 minus b, so it's minus 3. Okay, so like I said, this can be not a stumbling block, not a stopper, but something that might be a substantial amount of work. Usually book problems at this stage are set up to be not too bad because they're not assuming we have a lot of powerful methods for solving systems of equations. Okay, so remember what the whole deal was. It was the a, b, and c were the mystery numerators for this expansion, and I'm getting -2, +5, and -3. Ooh, and that's actually what I expected. Okay. So that means the integral of this guy, what do I have, 5 to 7, I think? Let me check that. Okay, I don't want to change the problem in the middle. dt is going to be the integral of all this stuff, dt from 5 to 7. Now, I've got a pretty nice situation here. This integral, these are all basically 1 over t kind of things. This is literally a constant times 1 over t. This is a constant times 1 over just t minus a constant, and here's t plus a constant. This is where it's kind of up to you or your teacher maybe to say, let's see, how much do you have to do? You're really sort of technically doing a small u sub to do this one and this one, but because t, it's just t shifted by a constant, it's not that complicated. I'm not going to do the u sub explicitly. Okay, I keep writing that, not wanting to do it. So this is going to be log of absolute value t from, let me put that in brackets, from 5 to 7. Okay, plus 5, and then it's just log of absolute t minus 3. That's all that happens. From 5 to 7. And then minus 3 times log of absolute t plus 4. 7, 5. Okay. So that's really not bad. And again, this is one of the simpler cases once you get this expansion of doing the integral, but it's really pretty cool. So that's going to be -2 times log. Now I set it up so that none of these these numbers would be negative. In particular, if this had been like a 2 or something, this would be a very suspicious integral. And in fact, it really wouldn't exist in any normal sense because you'd be going across where this has an asymptote. So it was important that this 5 was bigger than this 3. In any case, we're getting log 7 minus log 5 plus 5 times log 4 minus log 2 minus 3 log 11 minus log 9. Okay. Now, that's not a horrible answer, but we might want to use rules of logs. You often do. That's just one log. That's log of 7/5 plus 5 times log of 4 over 2, which is 2, and then minus 3 log 11/9. There are situations in which you'd want to actually combine these even more. Honestly, for a numerical answer, this is pretty good. But let me just remind you, with rules of logs, we could actually combine this into one big log. This is log of 7/5 to the minus 2 power. So that's otherwise known as log of 25/49 plus log of 2 to the 5th, which is 32, minus, it's going to get a little bit nasty, or let's say, minus log of, I'm just going to write it as 11 cubed over 9 cubed. I didn't contrive it to have this particular part be very nice. And so if you want it, it's log of big thing, 25/49 times a 32, and then divided by the 11 cubed over 9 cubed. And if you simplify all that, again, I'm just really showing you some practice with rules of logs. We could put the 49 on the bottom and leave the 11 cubed on the bottom, but put the 9 cubed on top. And I don't think it simplifies particularly well. Okay. If you want a number, here it is. About 2.19. So mainly the point was to get to around here where we really know, yes, we've got an integral, yes, we can get a number. And then it was kind of interesting to see with the logs. In other applications, like with differential equations, these last few steps can be really crucial because you're actually going to have stuff still with functions in them, indefinite integrals maybe, and you might have to do some more algebra with it, and the rules of logs actually really are important.